Okay guys, so today's going to be our second chi-square day, and we're going to do a dihybrid cross to start off. So there are, once again, we're going to work with fruit flies, and there's two different genes we're going to use. We're going to use the body color, which it could be black or red, and we're also going to use eyes, so they could have eyes or be eyeless. Now, if you look here, we are mating a black body eyeless one with a red body that has eyes. And when we mate them, all of the F1 generation has a red body and they have eyes. So this tells us that the red body is dominant and having eyes is also dominant, okay? So after we mated the F1 generation, so we mated two of them that are red and they have eyes. This was our numbers we got for the F2 generation. So we got 5,610 with the dominant trait. We got 1,881 with the dominant red trait, but the second trait is eyeless, so it has the recessive one. Third one, black, recessive trait, eyes, dominant trait, 1,896 of them, and then lastly 622 with both recessive traits. Okay, so that is going to be our observed phenotypes, okay? So those are our observed numbers. Now, if you remember for our dihybrid cross, because we mated two heterozygous individuals for both traits together, we should get a 9:3 to 3:1 ratio, okay? When you add the 9, 3, 3, and 1 up, you get 16. All right, so 9 out of 16 should be dominant. 3 out of 16 should be dominant recessive, 3 out of 16 should be recessive dominant, and 1 out of 16 should be recessive. So let me go back to those numbers, and we're going to add all these numbers up first. So we get 5610 plus 1881 plus 1896 plus 622. And we get a total of 10,009. All right. Now we're going to get some decimals here, guys. It's not a big deal. All right. But that is our total. So how do we figure out the expected? Well, what I like to do, guys, for the expected, and we're going to do red eyes first. I like to do and set up kind of a proportion. So we know that we should get 9 out of 16 red in eyes. Red eyeless, we should get 3 out of 16. Black with eyes, so we've got recessive and then our dominant. Once again, we should have 3 out of 16. And then lastly, black and eyeless, we should have 1 out of 16. Okay? Now, what I like to do here is set up a proportion. So we have 9 out of 16. And we got to figure out how many we would get out of our total. So what I do is, how many would be the 9? I'm going to put that on top, and then our total, I'm going to put on the bottom. Okay? How you solve this, guys, is you cross multiply. So I'm going to do 10,009 times 9. And I get 90,081. And I'm going to do 16 times x. Okay. Oh. Let me do that a little different. 90,081 equals 16x. And then we can solve for x by dividing each side by 16. And we get 5,630. Okay. Same thing with the second one. We're going to do the same exact proportion here. All right, so 10,009 times 3. We get 30,027 equals 16x again, where x is 1,877 approximately if we round. This one, it's the same exact proportion. So once again, and then the last one, we would just have 10,009 equals 16x. And we get about 626. Somewhere around there, depending on how you round, okay? So these are our expected values for everything, all right? And you guys can see how I solved that. I set up a proportion there, all right? So now let's fill in our chart for our observed. Those are our original numbers, okay? Our new numbers that we came up with, all right? From the proportions, we're going to subtract them. I know we get negative numbers here for some of them. It's okay, because once we square them, we're going to do that. Now, the last one, guys, make sure when you're doing the first one, you're going to do 400 divided by 5,630, and we get 0.07. For the second one, we're still using, the O minus E squared, but make sure you use the expected for that column or that row. Don't go back up here and use 5,630, all right? And when we are done, we get all four of these numbers. Now, chi-square is a summation. If you remember from our equation from last time, it is the sum, x squared is the summation of O minus E squared divided by E. Okay, so we have to add all of these four numbers together, all of our phenotypes, they all need to be added together. And when we add them all together, we get approximately 0.3 for our x squared value. All right, now, so our x squared value is 3. So far in the past, we have always been using that degrees of freedom as 1 because we only had 2 phenotypes. But in this one, for a dihybrid cross, we actually have 4 phenotypes. Okay, there's 4 of them. So we are going to be looking here, and you're like, okay, I can use 4 degrees of freedom. Now, remember, guys, degrees of freedom is our number of phenotypes minus 1. So we had 4 phenotypes. Subtract 1 from it, we are going to be using 3 degrees of freedom. We have a chi-square value of 0.3. So it is all the way over here. Okay? So that means that we would accept our null hypothesis. Okay? All right. So for that one, we would accept our null hypothesis. If I go back to our blank screen here, okay, if we wanted to write our null hypothesis, guys, okay, there is no difference between our observed traits. And there's a bunch of different ways you can write these, guys. I'm just giving you an example of it. For body color and presence of eyes, as compared to a 9, I'm going to say dominant to 3 dominant recessive to 3 recessive dominant to 1 recessive. Okay? So that is our null hypothesis, and because of that nice low number, we are going to accept the null hypothesis. Okay? One other thing I'm going to show you guys about the chi-square table here. If you're looking at the chi-square table, if you notice as we go down with our degrees of freedom, so like let me just use the 0.05 here, okay, for our confidence. So for 1 degree of freedom, it's 3.8. Whenever we go down to our dihybrid cross, which is 3 degrees of freedom, we have 7.8 as our number. Okay, so it went up from 3.8. What this means, guys, is if we have more degrees of freedom, in other words, more phenotypes in there, we have more room for error with still obtaining that 95% confidence level that we can accept our null hypothesis, because once we are on this side of the 0.05, what this means is we have a 95% confidence level that we can accept our null hypothesis, okay? But as we go down, we have a little bit more room for error with our degrees of freedom. All right, I'm going to skip this one, guys. Let me go to the last example here. Okay, you're studying horses, and you see that there are white horses, red horses, and a mix between the two roan. So what we're doing here, guys, is we're doing no longer regular complete dominance. For roan, if you guys remember, we kind of saw both of our phenotypes in the roan horse, if you remember from last chapter, okay? So we've got some data here. We got white horses, 524. We got red horses, 517. And we got roan horses of 1,031, all right? What we're doing here is we are mixing a white horse and a red horse together. And notice they are all roan. All right. So if we are doing a Punnett Square for this, I'm just going to use big R as being red. So we mixed a red horse and a white horse initially. And all of the offspring were heterozygous, okay? Then after that, what we did was we mixed two of those offspring together. And what we noticed was that we got this. So this one here would be red. This one would be roan. This one would be roan. And the last one, whoops, would be white. Okay, so if we want to do this for our expected, our red should be 25%. Our roan should be 50%. And then our white should be 25%. Okay, so there is our expected percentages. All right, so here is once again our table, guys. Whoops. I forgot to add a slide in there. Okay. So we have 524 white, 517 roan, and 1,031. All right. So let's do our expected. Okay. Go back here. 524 white. And red 517. Okay. So now, if we have this, guys, let's get our total. Our total, so we're going to do 517 plus 1031 plus 524, and we get 2,072. All right, so that is our total there. Now, what we're going to do is we got to figure out what our expected should be. So for red, we know it was 25%. So we have our total times 0.25. For our roan, that was 50%. And for our white, it was 25 again. So I get 518 for red, same percentage for white, so it should be the same number, and 1036 for the roan. All right, so red are observed minus our expected, roan, and white. All right, so for our observed, which is here, our expected, which is over here. For our red, we're looking at -1. For our roan, we're looking at -5. And for our white, we are looking at 524. I can't do mental math right now. It should be 6. There we go. Okay. So there are our O minus E's. Squared, we get 1 there. 25, or 5 squared is 25. And 36. And our O minus E squared divided by our expected. All right, so this one would be 1 divided by 518, which is 0.002. Second one, 25 divided by 1086, we get 0.024. And our last one, 36 divided by 518, 0.069. Add them all up, and we get 0.095 for our x squared value. Okay? Now, if we take that number, put it into chi-square, okay, 0.095. I don't care what our degrees of freedom is. We're going to accept it, but just so we know our degrees of freedom, how many phenotypes do we have? We had red, we had white, we had roan. So we had 3 phenotypes. Got to subtract 1 for our degrees of freedom, so we'd be using 2 degrees of freedom, and we'd be way over in this area here. So we would definitely accept our null hypothesis that our data is going to match that 1 red to 2 roan to 1 white for the color of the horse. All right. So there's a few more examples, guys. This one, you know, we're getting away from complete dominance. We're getting to the incomplete and codominance there, where there's going to be 3 different phenotypes. Okay. There's just a few examples for chi-square. You guys can try it on your own. Have a good rest of your day.